Hello, welcome on a sunny day for a change. There are 3 handouts. One of them is an update of the information sheet, labeled version 2. One of them is the next set of homeworks for chapter 3. And the third is another set of lecture slides. Homeworks were due today. They're up here for people here, and SIN students, I guess, are sending them out over the courier system. A couple of announcements. One is, and you would have known this if you've been reading the class news group, which you should be doing, is that the review sessions will be held as advertised on Fridays. They'll be physically here in Skilling 193, but SITN has changed the channel from E2 to E1. So people out on the network should beware of that. The first review session is this coming Friday, and it'll be an introduction to Verilog, which you'll be needing for doing the first programming project. Another announcement is that we still need graders. We have 1 or maybe 2. We could use 1 or 2 more. So if you're interested in grading, you get not to do the homework. You get to learn by grading other people's papers. You also get to earn, I think it's $8 an hour. So if you're interested in doing that, please see me or one of the TAs or Secretary Lilly. Grading is actually a fun thing to do, it turns out. And if we don't get any graders, I may be having the fun. Also the TAs. Okay, any other questions or comments or statements before we get started? What we've been spending the last couple of lectures talking about is the design of computers in general, and in particular the cost and performance trade-offs of various parts of computer design, trying to analyze when it is we ought to do something, how much performance you can gain from it, how much it costs you or might cost you to add a particular feature or change the design of an instruction set. What we're going to do now is bore down a little deeper into the design of instruction sets themselves, this very important layer in the computer hierarchy, which is basically the division between the software of the computer and the hardware of the computer. The first thing we'll do is try to figure out a way to classify the different instruction set architectures that have been designed. And really, if you look at commercial computers, there aren't that many. Probably in the history of computers, there maybe are a few hundreds of instruction set designs that have actually been built. Not thousands, certainly not tens, some number in the hundreds. Enough of them so that we can see the general categories into which they fall when you look at them in certain ways. So we'll do that, and we'll identify or try to identify the advantages and disadvantages of various of the features of those categories of instruction sets. And then we'll look in particular at a few in great detail and a few more in lighter detail. The example instruction set architectures we'll look at in detail are the VAX instruction set, which is an example of a complex instruction set, of the 8086 instruction set, which is an example of a popular instruction set, which may have no other redeeming features, and of a typical RISC instruction set. And we'll look at something which looks most like the MIPS, although many of them are so similar so that it hardly even matters. Although, in fact, we'll be talking about some of the elaborations on the various RISC processors that make them different from each other. And then we'll look at some measurements of instruction set usage of those instruction sets in real computers on real benchmarks and try to see what we've learned from their design and their use and map it back to our general classifications. This is all great and good stuff, and in fact designing instruction sets is lots of fun. The bad news is you probably won't get to do one. Real instruction set design these days happens on the order of about once a decade for significant instruction sets. Now that didn't used to be the case. It used to be the case that every new computer had a new instruction set until people recognized that the software burden that implied was so outrageous that it was necessary to stop inventing instruction set architectures at that rate. It also, even in these days of using C and C++ primarily for programming, it also is the case that binary compatibility is more important than was once thought. In the older days, people would design a new instruction set and expect everybody to recompile their programs and run them in the new instruction set architecture. Well, one of the problems turned out to be that many people in commercial establishments wound up, for the last 5 years, running a program for which the source was now lost. And you were trying to convince them to migrate their computer architecture from the old version to the new version. There was no way that they could run the old programs because they no longer had the old source. And in fact, it was standard in those days for every new architecture to come with a simulator program which was designed to simulate the old computer in such a way that the programs for which the source was lost could continue to be run. The problem, of course, is that in almost all cases, simulation of one architecture on another is slower than the original machine, even though the new machine by itself in its native mode is much faster. This kind of technique actually still exists, and you see lots of people trying, for example, to emulate Intel 8086 class architectures on other machines to get advantage of software that runs on those machines. In this case, it's not so much that the source code doesn't exist anymore, but it's the case that the source code is unavailable because it's proprietary, yet they still want to run the binary instruction set. So binary compatibility is one of the reasons why instruction set design doesn't happen very often. The other is that there is general agreement these days on what a good instruction set architecture should look like, and it's this kind of RISC machine. But I caution you into not to think that RISC is the last word in instruction set design. And in fact, these things wind up, like politics, happening in waves. And the current wave and the current politically correct instruction set architecture are the RISC instruction sets. But in fact, people are beginning to realize now that they too need to be elaborated for additional features and additional performance, and they're beginning to change. And 10 years from now, instruction sets won't be the same RISC instruction sets being designed now. I should also point out that if you were interested in designing your own instruction set architecture, probably sitting in this room is a pretty good thing to do, because if you look at the people who have sat in this room before, a fair number of them have gone on to, in fact, design significant new instruction sets. Two of my classmates taking 282 back in the 70s were the two primary architects of the Motorola 68000 series used in Apples and so forth. One of students at about that time, who I think probably took 282, is one of the primary architects at Sun and was responsible for a lot of the SPARC architecture design. Other people associated with this course, like John Hennessy, whose textbook we're using, was much involved in the design of MIPS instruction sets. So although the chances are you're not going to get a chance to do one, you're increasing the odds by taking a class like this, especially at Stanford. There are probably another half a dozen institutions around the world where that might be true. So what are the categories, or what are the criteria that we might use to classify instruction sets into different categories? Well, it turns out that the major one is how do you store variables when they're not in memory. Variables, almost all modern computers are in memory most of the time, but they need to be in temporary locations for operation. And the question is, where are those stored? Well, you could in fact choose to store them nowhere and have nothing except memory, and a memory-to-memory architecture is an example of a machine that does exactly that. The most popular older machines, though, are ones that had a single accumulator, basically a single temporary storage register in which all arithmetic operations were done. And we'll see details of that in a second. A third kind of computer is a stack-based computer, where instead of having a single accumulator, you generalize that accumulator to a kind of structure that can hold multiple operands at once, but in a very limited way. You have access only to the one on the top of the stack. Well, it turns out that that is fairly limiting. So another more general way, which turns out to be the most popular these days, is a register set based, which is sort of like a stack that you manually manage, that you have multiple registers, all of which can store temporary variables, and you access them in random order. Another measure that you can use to apply to most of these is, for each particular instruction, how many explicit operands does that instruction get to name. For a stack-based computer, for example, you need to name no explicit operands because they're all implicitly on the stack. For some of these other architectures, you in fact have a choice about the number of explicit operands in an instruction, and we'll see what those are like. Another classification category is this RISC versus CISC dichotomy, which is how atomic or how complex are the operations that you're going to provide. And that has significant trade-offs for both the ease of compilation and the ease of implementation of high-performance computers, which we'll see. Another issue is instruction encoding. Once you've decided on the basic organization and complexity of the instructions, you've got to figure out a way to encode them that is both convenient and efficient. Branch architecture is becoming a more and more important part of the architecture classification, because branches are one of the things that turns out makes it very difficult to make high-performance computers. If we only did not have to branch, then many of the computers could be a lot faster than they are. But, of course, computers make decisions, and branches are the mechanism by which they make decisions, and we have to look carefully at the way that part of the architecture is designed. And then there are sort of the more exotic features, memory structuring features, some of which, like caches, ought to be transparent to the instruction set architecture, but sometimes are not. And others, like virtual memory and paging, which are very much involved in at least operating system level programming. In addition to memory structuring, the operating system is also concerned with the other features of the instruction set architecture that have to do with protection, processes, tasks, and all of that mechanism. Let's look at one at a time the various instruction architectures with respect to how they treat temporary operands. The accumulator architectures were the original old machine type architectures. There was typically a single register for holding temporary results. Often, in fact, there was a pair of registers, but they had special purpose functions. So in many machines, for example, there might be an accumulator whose width was the size of a word in the machine, and then another register for holding multiplier and quotient parts of operands, because multiplying two 32-bit numbers, for example, can produce a 64-bit number, and there needed to be some way to store the entire 64-bit quantity. But these weren't general-purpose registers. They were explicitly used, or rather implicitly used by instructions that knew that register pairs had to be used instead of a single register. It was typical in these machines for each instruction to have only one operand. So a sequence of instructions to produce the sum of B and C into A would be something like this. These mnemonics are in fact 7090 mnemonics from the IBM machine, which was popular in the late 50s, early 60s. This is clear and add B, which is to say clear the accumulator and then add to the accumulator B, which is another way of saying load. In fact, it was exposed as clear and add because that's the way internally the machine actually implemented that function. The instruction format simply had an opcode of a certain number of bits and a field which was big enough to contain the entire address of the operand, B. So it would load B from the address indicated by the bits in that part of the instruction, put it into the accumulator. Same thing for add, would fetch C, add it to the accumulator, and store would take what was currently in the accumulator, store it into the address specified by the instruction. Notice that this kind of fixed width instructions in simple decoding format is exactly the kind of RISC-like instruction that we'll be seeing later and that you probably are already familiar with. In many ways, the very early machines can be viewed as a kind of RISC-like machine. One of the things that this didn't have, that RISC machines do have, are a whole variety of registers into which you can store temporary results. In this case, it only had a single register. They also typically had additional fields for other things. On the 7090, this was a field that was used, for example, for indexing. And there were, in addition to these operand registers, a set of index registers that could be used to compute addresses in the case where the address of the operands are not known at compile time, or for accessing multiple variables which represent parts of an array. So what's good about this? Well, instructions are generally short. An opcode plus an address and a few additional bits is all you need, and they're often very fixed with kind of structures. In fact, on many of these machines, memory was not even byte addressable, so the instruction would typically fit into a single word which had a unique address, and there was no subdivision into individual bytes. It's easy to build these machines. They have minimal internal state. You only need to store the accumulator and the quotient in additional indexing registers. So they're simple. The problem is, or one of the main problems, is that the traffic rate to memory is extremely high. There are lots of loads and stores. When there are temporary results to be produced, there's no way to save them unless you store them back into memory, which takes an additional full instruction plus traffic to memory. So it's a machine which works out well when the instruction execution unit is not that much faster than the memory. But in these days, when instruction execution rates and CPUs are so much faster than the memory, having this kind of high memory traffic design is a bad thing to do. Nonetheless, it was a very popular kind of design. The IBM 7090 was the premier scientific computation machine back in those days. The DEC PDP-8 was one of DEC's early mini computers, also designed for scientific computation that used this kind of design. The MOS 6502 was a machine that was one of the first microprocessors on a single chip and was used in the Apple II and was probably at that point the single most successful computer architecture in terms of number of computers shipped to date. Well, if one register is good, maybe no registers is better. And in fact, the stack architecture is one example of architecture which has no registers. Everything is done in memory in a very kind of stylized fashion. I'm sure you all know how stacks work. In order to evaluate the expression b plus c times d, you push b onto the stack. Let me draw a stack here. Then push c onto the stack, then push d onto the stack. Stack is growing up in this particular case. Multiply. Now notice that multiply is an ALU operation but takes no explicit operands in the instruction at all. Implicitly, the operands for multiply are the two operands that are currently on the top of the stack. So multiply takes d and c, wipes them off the stack, and replaces them with the result of the ALU operation, c times d. Same thing for add. It takes the current top two elements of the stack, which is c times d and b, and replaces them with a new top element of the stack, which is b plus c times d. And then pop A takes whatever is in the top of the stack, stores it into memory. This is the equivalent of a store operation plus removing things from the stack. If you own HP calculators, at least the older HP calculators, this is familiar to you as a kind of reverse Polish notation. Do HP calculators still do that, by the way? Modern ones? Okay, so everybody knows how to do reverse Polish. Although, from my point of view, it's not a desirable architecture for a calculator. It doesn't happen to fit the way my mind works, because I grew up, and most people did grow up, with operator precedence languages rather than reverse Polish languages. But be that as it may. What are the advantages here? Well, very short instructions are possible, at least some of them. The ALU operations have implicit stack addresses and no explicit memory addresses. So you wind up getting the effect of having multiple registers without either having to name the registers or having to load them from memory. The compiler is easy to write. The technology for taking an arbitrary priority operator expression and turning it into a kind of reverse Polish is pretty trivial. So that's the good part. What's the bad part? Well, the code is very inefficient. One problem is that there's no way to do it's very difficult to do optimizations that compilers like to do, like common subexpression elimination. If, for example, I had an expression that was an array reference with a subscript like I times 3, and then I'm going to operate on that with another array reference with an identical subscript, it would be nice to be able to compute this I times 3 once, save it somewhere so that it can be used 2 different times for the 2 different array references. Well, there's no convenient way to do that in a stack architecture. You could compute it, you could store it into memory, and then load it back into memory, but that's a lot of memory traffic and might in fact be more than you saved in doing the computation. Well, you can fix that. There have been proposals and implementations of stack architectures that allow you, for example, to compute an intermediate expression, to duplicate it, so you wind up with 2 copies of it on the stack, And then, in fact, later on to randomly access stacked values. If the stacked value that you want happens not to be at the top of the stack, but it was a pushed value that you saved from earlier, you might be able to have an ALU operation that says, don't add the top two elements of the stack, but add the top element of the stack and the stack element underneath the next element. Well, what you're really doing is creating a random access to the top few elements of the stack, which begins to look very much like a multiple register implementation, and in fact, that's what it is. The other problem is that the stack itself is often a bottleneck, and if it's implemented in the normal fashion by having simply a stack pointer as a register and the stack itself in memory, then we're back to the case where the stack is a bottleneck by being a memory access. Well, you can fix that too. There have been very clever implementations that treat the top few elements of the stack as special by putting them in registers, basically by caching them into high-speed storage rather than putting them into memory. But it gets very complicated because the stack, unlike a register set, has an infinite number or unbounded number of locations. So it's very difficult to design the schemes which efficiently dump the stack to real memory when it gets too large and pull it back when those pops have been done that require old elements on the stack. The other problem is that it's often the case that a single stack isn't enough. We've been talking about a stack primarily for expression evaluation. Even that has a problem because that stack may be required to hold different types, integer versus floating point operands versus character operands. And then what do you do when you say add? If there's a floating point operand and a fixed point operand on the stack, does the add instruction know that those are two different types? Do you mark the stack data with a tag to indicate what type it is? It begins to get very complicated. In addition, there are other kinds of stacks. There's a stack that's used for control transfers, for doing subroutine calls and returns. And then there's another kind of stack which is used for variable storage. In modern languages that have dynamic storage allocation on procedure entry or that allow recursive procedures, you need to have some kind of a stack-like structure in order to be able to hold those local variables. Well, here are three different stacks. Are they the same stack? Are they different stacks? Stack architectures quickly become very complicated. There aren't too many examples of successful stack architectures, and none of them are pure. The original, most purest one is probably the Burroughs 5500 machine, and these machines had limited popularity. Notice that although generally speaking we've abandoned stacks for the use of expression evaluation, stacks are still in use for control and for variable allocation for functions. Although, generally speaking, the instruction set architecture itself doesn't have anything in it to support those stacks except perhaps a simple push and pop type mechanism. Most of the complication of that stack architecture for control and function variable allocation is done by the software. Although we'll see at least one example of a machine where a great deal of that kind of stack manipulation was in fact embedded into the instruction architecture. Okay, here's another example of an architecture that has no registers. Registers are complicated. Let's get rid of them. Memory-to-memory architecture. Every operand reference is explicitly noted in the instruction. And in fact, you can have either 2 or 3 explicit operands per instruction. So one way, for example, to implement A equals B plus C is to have a simple machine language instruction that does add and names those 3 variables. One of the problems with this, of course, is that the instruction gets very long because this may be, let's say, 3 32-bit values to specify the 3 operands. A compromise might be to allow only 2 operands per instruction, in which case you wind up having a destructive ALU operation. So in order to get the equivalent of A equals B plus C, you first have to move one of the operands to the target location. This moves B to A, and then add into A, which is now the value that B was, C, to get the sum of B and C into A. Another alternative. So what are the attributes of this? Well, the instructions are very long, but on the other hand, the code is very compact because there's no waste for things that really don't have any correspondence with the source language program after all. the register designators. In fact, I remember people writing papers decrying register-based machines because registers were arbitrary things foisted on the compiler writers by the hardware designers, and they had no correspondence to anything that was in the source code. Why are we bothering with them, and why do compiler writers have to worry about them all the time? Well, in fact, there's a good reason why they have to worry about them, and that has to do with making efficient programs. But the easiest kind of compilation and the most compact code, because it doesn't reference any of those registers, is this kind of memory-to-memory architecture. But again, memory is an extreme bottleneck. You don't wind up having registers that save temporary values that you can use for common subexpression elimination and those kinds of optimizations. So these machines are not popular anymore, certainly. There was a time in the old days when they were fairly popular, but mostly for non-binary arithmetic. It was very common, and in fact it still is common to some extent now, to have data types that allow you to store directly decimal arithmetic. And in fact, in those cases, the size of the data is unknown at compile time or even at execution time. Any particular number might be n bytes wide, which makes doing stacks or register machines extremely problematical because you don't know how big to make the register or how wide to make the entry on the stack. So in fact, memory-to-memory architectures are perfect for that sort of thing. The IBM 1620 was a BCD machine used primarily for scientific computation that had memory-to-memory architecture. The IBM 1401 was the equivalent kind of machine for doing business operations, which also used BCD. And even in more recent machines like the IBM 360 and in the VAX, memory-to-memory architecture instructions tend to be a subset of an existing register-like machine. In the case of the 360, it was used exactly for this reason, to do SS instructions for either strings or for decimal data. And in a complex instruction set like the DEX-VAX, which we'll look at in detail, memory-to-memory architecture is used even for regular binary operations as, I would say, a convenience to the programmer or to the compiler writer. Yeah?
What was the motive for decimal number storage?
What was the motive for decimal numbers? Well, one of the motivations for decimal number storage was that there aren't any rounding errors. And if you try to represent certain numbers in binary, they turn out to be repeating fractions, which they aren't in decimal. So, in fact, the business community was very excited about not losing that last tenth of a cent in any of their computations, and in fact did and still do a lot of their computations in decimal. Binary machines are ubiquitous now, but that wasn't necessarily the case. Early machines often were decimal or biquinary or other base number systems. In fact, I should bring this in. There was even a proposal back in the early days to do a computer based on base 12 numbering system. And there was a sort of kook group in the East Coast called the Duodecimal Society of America, who proposed that not only should you design computers based on base 12, but we should all be doing arithmetic in base 12. And they had some interesting propaganda demonstrating why base 12 is a much better number system than base 10, and we shouldn't base our arithmetic on the fact that we happen to have 10 fingers. They weren't too successful, and neither were base 12 computers. The last style we'll talk about turns out to be the winning style and the architecture that most current computers are built out of, and that's the register-based architecture. And the idea is to have several, where several can be defined as any number from 4 to 64 or 128, of mostly equivalent accumulators. And this is very much like the accumulator style architecture we saw before, except that there are more of them, and you have to say which ones you want. One way of viewing registers is that they are very much like a cache for recently used values. And the difference between registers as a cache and the cache memories that we'll see more of and have seen before is that registers are explicitly managed. The programmer or the compiler needs to indicate when it is things should be brought into this register cache and dumped from this register cache back into main memory. But that's really all they are, is a way to get access to a small amount of very fast memory which can be addressed with a very small field in the instruction rather than a big field as you need for a memory operand. Given the register architecture, there are a couple of options we can choose. One is we can choose to have 2 or 3 explicit operands per instruction. As we saw before, in the memory-to-memory architecture, you can add 2 things and put it in a third location, or you can add 2 things to something that's already there and replace that something that's already there, which has the effect of destroying an operand, but the instruction is shorter because you're only specifying 2 things instead of 3 things. Another choice you get to make is whether or not ALU operations can have memory accesses. And typically for the CISC machines, for the complex instruction set machines, the answer was yes. So you could write an instruction sequence like this for A equals B plus C. Load into register 1 the memory location B, add to register 1, destroying register 1, notice, the contents of the memory location C, and then store register 1 into A. Short 3-instruction sequence. Most of the RISC machines, and we'll see reasons why later, don't allow ALU operations to reference memory. So what you need to do is, in fact, expand that into the following sequence of loading 2 separate registers with the 2 memory locations, and then adding those 2 things together into typically a 3rd register for RISC machines, and then storing that into memory location. You've added an additional instruction. You've now simplified the add instruction since it denotes only registers for its operands rather than memory locations, which gives you, incidentally, more space. So it's typical for a RISC machine to make this choice, which is no memory operands, and this choice, which is 3 operands per instruction. And we'll see some examples later of why this is, in fact, a very useful thing to do. As I said, register-based architectures are the thing these days. It's the dominant architecture from everything going back to the 60s with the arguably first RISC machine, the CDC 6600, the IBM 360, which was certainly the most popular mainframe machine, PDP-11, one of the best mini-computers, 68,000, and all current RISC machines. The advantages, we've mentioned some of this before, it allows fast access to temporary variables. It permits, some people would argue requires, compilers to be clever and do clever optimizations to manage this cache of recently used values. And because there is a cache, as in all caches, it reduces the traffic to main memory. What are the disadvantages? Well, instructions tend to be longer because you've got these fields in the instruction that now have to designate which registers are being referenced. So instructions are longer than accumulator designs. They're shorter than memory-to-memory architectures, obviously. The other problem, which can be a big problem or a small problem, is that now context switching is more expensive. Remember that all computers these days run multiple jobs or multiple tasks at the same time and periodically have to switch from one to the other. That switching involves saving all of the machine state that currently is not in memory. Well, in a register-to-register or in a register set-based architecture, that machine state includes all of the registers. So anytime you take an interrupt or switch from one task to another, you've got to dump all of those registers into memory, reload them before you can switch to the new process or to the interrupt routine. We'll see some examples of RISC machines, namely the Spark architecture, which has taken the number of registers to an extreme, to a point at which context switching becomes an extremely expensive operation. Comments? Questions? This I think we've actually talked a bit about. The question is, for general purpose register ALU instructions, what are the operand types? Well, you can choose to put no memory addresses in the ALU operations, in which case they're register to register only. It typically requires bigger encoding, but simplifies register allocation because you don't destroy a register by doing an operation, which makes it very easy to do code generation. And as we'll see later, it makes it very easy to pipeline the computer, which is a technique we'll look at in detail for speeding up the execution. The downside is that there's a higher instruction count, typically, because you need to have a separate instruction to load the memory operand into the register. The alternative is to have, or at least allow, a single memory address in the instruction. It's typically the case that these kind of register-to-memory machines, like the IBM 360, also have register-to-register operations. So in many ways, the one-memory address architectures are a superset of the no-memory address architectures. Well, those are the trade-offs in deciding about registers or the lack thereof. All of these architectures, though, have to access memory somehow. And what I'm going to do now is go over some of the various different ways in which you can specify inside an instruction what memory location to reference, or if it's not a memory location, where else the operand is coming from. Of this list, the first two are non-memory operands, and the rest of them are memory operands. And the simplest non-memory operand is a register designator. Very simple to encode in the instruction. You put a few bits in the instruction indicating which register number. The operand is, in fact, the contents of that register. Or if it's a destination, it means that the destination value should be placed in that register. Simple enough. The next non-memory kind of addressing mode is an immediate instruction. You encode within the instruction itself the value of a constant to be used as a source operand. Now, obviously, this is sources only, not destinations. You can't store into a constant. This has a problem, or at least some considerations. One is, what's the type of that constant? Is that type implied by the opcode? Well, probably is. But what about the length of that constant? Is the length of the constant implied by the opcode? Could be, or maybe it's not. Maybe you need additional specifiers to indicate the value of the immediate field. The advantage of immediates is that it saves having to load a constant from memory. You can design a computer which has absolutely no immediate instructions whatsoever, and anytime you need a constant value, simply load from a memory location which has been preloaded with that constant. We'll see later on from some instruction statistics that from a performance point of view that would be a poor choice, because many instructions use immediate fields and therefore save an additional reference to memory. Okay, what if we want to reference memory? Well, a direct memory address within the instruction is the simplest thing to do. You simply put inside the instruction the absolute address of the memory location to reference. Popular for very simple kinds of programs, useful for getting at global data, but it turns out that, in fact, much of the data in modern programs and modern programming languages is not at fixed locations and is dynamically accessed and is not known at compile time or even at length or load time. So this is not typically a very popular kind of memory access mode. More popular than that is register indirect, where the contents of the register contains the address of the memory location to reference. You'll see indirect and deferred used in essentially the same way. This is also registered deferred. So somehow at execution time you've got to arrange to put within that register the address of the memory location you want to reference. Displacement addressing is a variation of that, where in addition to taking the contents of register 1, you add to it a constant which is in the instruction. So in fact, register indirect is a subset of displacement mode where the displacement is 0. This kind of addressing is very useful, for example, for references to a stack. If you've done, as I alluded to before, variable allocation on the stack, because you have to do that at procedure entry, if R1 is your stack pointer, then 100 might be the offset from the current stack pointer, indicating the variable to be referenced. The next elaboration over that is adding the contents of two registers together, either with or without a displacement, which is to say either with a displacement of 0 or not. No, actually, I said that wrong. You can do index in several different ways. One is that you can add the contents of two registers together. The other way is that you can add, I guess I said it right, and in fact the notation is wrong here. Well, it's more complicated than that. Actually, there can be a variety of forms of indexing. One is that you take the contents of two registers and add them together. Where might you want to use that? Well, let's say that you're accessing an array on the stack where R1 is the stack pointer and R2 is the computed offset into the array that you want to access that variable at. What I had originally written here was a large constant meant to refer to a memory address and then index that memory address by R2. One of the questions about displacement form addressing is how big can that displacement be? Is that simply a small constant indicating an offset off of register 1, where register 1 is really pointing to the memory location? Or can that displacement be as large as a memory address, in which case you get this form, where you're adding what probably is a smaller number, an index in R2, to a larger number, which is a constant in the instruction, which is the base memory address of that variable. And really, these two are the same kind of memory access mode, and the difference is whether you consider the constant to be a small offset or the constant to be the address of the memory variable itself, or at least the base of the memory variable. In any case, both of these schemes basically are the way to take one or more registers, add their contents, and add to that a constant which comes out of the instruction. I hope I wasn't too confusing there. Any questions about those modes? The next elaboration is scaled indexing, and that takes notice of the fact that for doing array indexing, if you're doing something like A sub I, if A is a 4-byte array, which is to say it's a collection of elements, each of which is 4 bytes long, and you want to reference A sub I, you can't just use one of these indexed or displacement modes and put I in the register and use A, let's say, as the displacement or as the base of the variable, because you've got the first multiplied by 4. Well, you can do that in explicit instructions. You could load I, multiply it by 4 to get the byte offset within that array, and then use one of these other forms to add the base of the address. Well, scale does that for you, and in fact it's typically a memory mode where you add a constant from the instruction, which is either a small offset or could in fact be the base of the array. You add another register, which might be, let's say, the stack pointer, if this is an array that's based on the stack. And then you add a third quantity, which is a register containing a subscript expression, and then the instruction automatically multiplies it by the width of the elements in that array. And typical architectures that allow scaled addressing allow that number to be 1, 2, 4, or perhaps 8. Notice that it's almost always a number which is a power of 2, so in fact the implementation of that instruction in the hardware can be a simple shift of that register before adding it to the other register. Memory indirect is a way that says that once you've done any of these other things, you can in fact say that that memory location is itself an address and not the operand to be referenced. So that says, for example, in this case, that register 2 contains the address of a memory location. Go to that memory location, take its contents, presumably a word size quantity, and use that in turn as the address of a memory location. A very good way to do indirect tables, some kinds of pointer lookup, that sort of thing. Notice that, in fact, it can be, and it has been in architectures, that the location that you reference with that first memory specifier can itself specify something in memory, which is a memory specifier. So instead of just being the address of an instruction address, or the address of an operand address, it could be the address of something that looks like a little bit of an instruction, which itself says how to do the next level of memory indirection. And in fact, there are machines that were designed that allowed a single instruction to take an arbitrary number of cycles by chaining through memory to look for subsequent memory indirects until it found a memory addressing mode specifier that says this is not indirect, you can stop now and access your operand. Makes the instruction extremely hard to pipeline. Last kind of memory address mode I'll talk about are the auto-increment and auto-decrement ones, where you use the contents of a register to point to a memory location, but then either before or after referencing that location, you increment or decrement the contents of that register. useful for stepping through an array, for example. In particular, if the addition is done not necessarily by 1, but by a value which is the size of the operand being referenced, then you can step through elements of an array without ever having to increment the pointer. The VAX and the PDP-11 were famous for these kind of auto-increment and auto-decrement operations. Notice that it's very typical for auto-increment to reference the memory location through the register first, then increment the register afterwards, and for auto-decrement to do the reverse, to decrement the register first, then to access the variable that that register points to. Why? Anybody know why those things should be designed asymmetrically?
For stacks.
Exactly, that's the answer, for stacks. If you're trying to use that register as a stack pointer, auto-increment allows you to push something on the current, well, you can do it either way, but let's say auto-decrement allows you to push something on the stack by first decrementing the stack pointer, then storing the location there. When you want to pop something from the stack pointer is pointing to the last pushed element on the stack, so you pull it off the stack first, then you increment it to remove that item from the stack. So these work well in tandem to implement a stack using any general purpose register. In addition, any of these memory addressing modes, in theory, could be used in PC relative forms. And in fact, in a computer like the PDP-11, the PC is just one of the general registers. So any of these instruction addressing modes, if they specify the register which happens to be the program counter, does addressing relative to the program counter, which allows you to do things like position-independent code, where the references to the data moves along with the code when it moves in memory. Obviously, these complex modes are all useful in some instances, and they reduce the instruction count when you get to use them, but the cost of implementation of these modes is extremely high. Yeah?
So how exactly are these modes used then? I mean, they're sort of built into an instruction architecture?
Yes, these are built into the instruction architecture and, in fact, built into the encoding of the instruction. One of the things you've got to choose, and that's the next slide, in designing your instruction architecture is how, in the encoding of the instruction, to indicate to the processor which of these instruction modes is being used. And those modes are, in fact, executed by the hardware, implemented by the hardware. Was that the sense of your question?
Yeah, I was wondering how much the hardware paralleled the access mode. If this was a direct reflection of the way the hardware was put together, or if it was just part of the sort of the microcode of the instruction set, or what?
Well, you're asking a couple of things at once there. When you talk about microcoding, you're talking about a particular implementation technique by which the hardware might choose to do these instruction modes. But the general answer is yes. These are, if you choose to use them, like the VAX did, those are in fact the instruction modes that the hardware somehow has to support. It's not just an artifact of the software. That's what you're asking the hardware to do.
So for instance, where it was adding together or multiplying times 4, that would be sort of hardwired in somehow.
Yes, that would be hardwired in. You would have to indicate in the instruction that what you wanted it to multiply by was 4. And that could be implicitly part of the opcode, or it could be separate bits in the instruction somewhere that indicates that you want to do that. But that has to be in there somewhere so that the hardware knows which of those modes you want to use. In fact, that's talked about a little bit here, that in encoding which of those addressing modes you're using, you could implicitly put it in the opcode, or you could explicitly, when there's a large number of modes, use a separate byte or field within the instruction to indicate the address access technique that you want to use. I think we'll skip over this part of this here. Now this is an embarrassing slide. It's an embarrassing slide because we have to talk about it because it exists in the real world, but it shouldn't be the case. And this is this issue of big endian versus little endian memory layout. It's caused no end of headaches because computer designers in their infinite wisdom have made two different choices for what essentially represents an arbitrary convention for storing multi-byte pieces of data. Let's say that we have a word which is meant to contain a 16-bit value, which in hexadecimal is represented 11223344. Now, if this were a word-oriented machine where each word contains 32 bits, then there's no problem about memory addressing. That word has one address, and there's no issue of which part of the word it's addressing. But all current machines are byte addressed, in which case you've got to decide, when you divide this into bytes, which order those bytes should be stored. Well, little endian stores the littlest end of the word first, and then ever-increasing bytes of the word in that direction. So location x has 44, x plus 1, 33, and so forth. The big endian convention does exactly the opposite. The first byte is the first most significant byte of the word, and they decrease from there. It really doesn't make any difference. Unfortunately, both conventions have been used by popular machines. It doesn't have much of a performance effect. It does have a major effect on exchanging data between computers that use the two different formats. And interestingly enough, it is not something that's easily fixed by recompiling, because it's very easy and in fact common for people to write C language source code that depends on the memory convention used for storing large operands. One example of that is, one example are unions. Anytime in C you write a union that overlays smaller items with larger items, then the order of the bytes within that larger item becomes significant because the smaller items will be different. Another simple expression that demonstrates that is that if I have a pointer to a long integer, for example, and I recast that pointer as a short integer, I assume you all know enough C to understand what this means. What this does is say that P normally points to a long integer, let's say a 4-byte integer. I want you to interpret P as a pointer to a short integer and take the contents of that short integer. Well, that takes the first 2 bytes of the variable pointed to by P, which might either be 1122 or 4433, depending on which machine you happen to have compiled your C code for. So it's a major headache, an architectural non-issue, but a practical issue. I see people still bringing up homeworks here, which is fine. Remember, the homeworks are due end of class today. This is an issue which I've beaten you up about before. Make one final attempt at convincing you that it's important. Provide enough address bits in your instruction set architecture for the expected lifetime of your machine. Remember that it grows at about 2 bits every 3 years or maybe more, 2 to the t minus 1962. And there are lots of good examples of this transition that was done extremely painfully, sometimes in multiple steps. The Intel 8086 first came out, I guess actually the 8080, came out with 16-bit addressing, extended later to 24-bit addressing, actually extended from the 8080 at 16-bit addressing to 20-bit addressing in the 8086, to 24-bit addressing in the 286, to 32-bit addressing in the 386. And every one of these transitions was extremely painful to make. IBM did it in having 24-bit addressing for the 360, later extended to 32-bit addressing, which they originally thought would be an easy transition. Turns out, as I mentioned in a previous lecture, to have been a harder transition than they thought. I think people are getting the idea. And even machines now that are designed with 32-bit addresses, like the MIPS R2000, were designed in such a way that the extension to 64 bits of addressing in a machine like the R4000 is a lot less painful than any of these other transitions. And whether 64 bits will really last us for another 40 years is anybody's guess. Floating point operands. Just want to go over this briefly. Basically, you have several different choices. One is that you can choose to use the same register file that's used for integers for floating point operations. Well, that's useful because you don't have to have a separate set of registers, so it takes less hardware, which means that you can use that chip area for something else, for making your machine go faster, or caches, or whatever. It's simpler to program because you don't need to move from the integer register file to the floating point register file. You still need to do converts, but you may not need to do moves. If you have a separate register file, though, you may be able to get higher performance because you can have special purpose data paths for the floating point execution units that go directly to the register files. And essentially what you're doing is giving a private register file to each of the execution units, one to the integer unit, one to the floating point unit, which gives you a higher bandwidth for registers as a whole. A third approach is, in fact, not to use a register file at all, but to go back to a stack design. Remember that stack designs were reasonably good for certain kind of expression evaluation, and floating point operations are mostly expression evaluation, so why not use stacks? The Intel 8087 is an example of an architecture which is basically a stack machine with, again, some of the elaborations we talked about that stack machines find convenient to do what amounts to some kind of register memory instructions for the stack. So the major point is that the choice for floating point operations and the choice for fixed point operations don't have to be the same. You can make those independently. Okay, branches. Branches are becoming more and more important because of the performance effect of being able to implement branches successfully. So let's look at 3 different ways conditional branches might be arranged. The first one, and the one which probably dates back farthest in time, is condition code. The condition code is essentially a small register. It's a piece of state information in the machine that's set by, well, maybe not all, but by most operations. It's often done as a side effect of an instruction. Let's say you do an add instruction, you might set the condition code implicitly to indicate whether the result of that add instruction is positive or negative or 0. Condition codes, and then the following branch instruction, let's show how that works. The following branch instruction would test the value of that condition code. So let's look at, for example, a condition code machine, condition code architecture. You would do something like compare register 1 and register 2. That would implicitly set the condition code saying whether those registers are equal or which one is greater than the other. And then you might do, in a subsequent instruction, a branch greater than or equal to some location. So this is example 1. Well, one of the problems about this is that there is now some hidden state information, namely the condition code, that is valid between these two instructions. Condition code here must be preserved. And we'll see later that one of the techniques for increasing the performance, especially of pipeline machines, is the ability to reorder instructions, and in fact to insert between 2 instructions like the compare and the branch other unrelated instructions that basically fill up time. It's very difficult to do that in a condition code architecture because chances are the instruction that you're going to insert in here is going to destroy the condition code that was set by the compare. Nonetheless, condition code was and still is a very popular scheme for doing branch instructions. Certainly the IBM 360, 370 series had it. The Intel 8086 architecture has it. The VAX had it. And even a RISC-like machine, the SPARC architecture, has it, although in later variations of the SPARC they've made some changes that allow you to avoid the use of condition codes in some cases. One of the problems with condition codes is that you've got to be very careful in deciding which instructions should set the condition code and which instructions should not. For example, in the 8086 architecture, INC and DEC, the increment and decrement instructions, do not set the condition code. Can anybody guess why they might have chosen to do that? It has to do with not destroying the condition code when it's in use for something else. The original heritage of this instruction set had very small memory operands, 1 or 2 bytes. And if you wanted to do multiple precision arithmetic, you had to preserve the carry instruction from one add to the next. So if you were adding 4 bytes, you had to do it 2 bytes at a time. In order to address the next set of bytes, you had to do the increment and decrement for the pointer, to be able to point to the next set of bytes or set of words to be added. If increment and decrement destroyed the condition code, you would lose the carry information that you had saved by doing the first add. So either you couldn't use increment and decrement for pointer arithmetic to access the operands, or you had to save and restore the condition code around the increment and decrement. So their choice was, for example, not to have the increment and decrement change the condition code. Makes this kind of architecture difficult to use. The alternative is to put conditions in a general register. What that basically does is take the condition code out of this sort of magic implicitly set state information and put it into a register just like all other state information, or most other state information, where the programmer has explicit control about where it goes and when those conditions are set. So going back to our example, if we had a condition code in register machine, you might do something like compare, again register 1 and register 2, but this time put the result of the comparison, let's say 0 or 1, in a third register. And then sometimes later, you might say, or in the following instruction, you could say, branch if register 3 is 0 to whatever location. Notice that there's no hidden state information in between these two instructions, which allows you, or allows the compiler, to schedule other instructions within there that don't affect the sequence of the compare and the branch. One of the disadvantages of this compared to the condition code architecture is that it winds up sort of using up a register. You just wasted a register that otherwise you might not have to use. But these machines that implement condition code and register architectures tend to have lots of registers, like the MIPS and the DEC alpha. A third kind of architecture is one that allows you to basically combine the compare and the branch in a single instruction. Rather than having to save the result of doing the comparison, either in a register or in a condition code, you just do it all at once. And you do something like, let's say we have a compare branch architecture. You do a single instruction that does something like compare and branch if equal by comparing register 1, register 2, if they're equal, branch to location. Well, this looks great. Single instruction, saves space, might even be faster to execute, but it's a more complex instruction. In fact, this is a case that we looked at in an earlier lecture where we decided to try to combine an ALU operation and a branch instruction into a single complex ALU and branch instruction. The result in most machines will be that you have to lengthen the time it takes for instructions to execute, or certainly this instruction to execute, and it may not be a worthwhile trade-off. There aren't too many machines that have these kind of complex branches, especially when the comparison operation is general. The VAX is an example of one that does. Any questions? All right, let's talk a little bit more in general about RISCs versus CISCs. I'll go over this quickly because we've probably talked about it in various bits and pieces throughout. Generally speaking, RISC architectures have fixed instructions. They're typically 32 bits wide. They are register-based machines, general register machines with 32 or more registers. They only have load and store operations to memory. None of the ALU operations have memory operations. They often, although not exclusively, don't support complex data types, strings, decimal instructions, and so forth. And they try to avoid special case instructions. They try to make it orthogonal in the sense that any operation can be used with any register and to avoid registers which are special purpose and more difficult for the compiler to schedule the use of, although they compromise on this as well. The other kind of feature is that they're willing to make architectural compromises to allow efficient pipelining or to allow efficient compiler optimization. For the more complex instruction sets and the older instruction sets, people were very concerned about making the instructions look good to the assembly language programmer and easy to use for the assembly language programmer. Well, these days there aren't any assembly language programmers anymore, or hardly there aren't. So you're willing to allow the instruction set to have certain architectural warts in order to make it more efficient or better for the compiler. Now, why is it that for what, 25 or so odd years, people were making instruction sets which were ever more complicated. And these weren't dumb folks. These were people who were pretty smart and had an argument that said that, in fact, making instructions complicated were better. Well, what were those arguments? Well, one is that the more complicated instruction set you design, the fewer instructions you need. The density of code is therefore higher. The program is smaller. You have to access memory less time. Well, this is true, although the density of instruction sets insofar as the amount of memory space you have is no longer a consideration because memory is really cheap. There is an issue of low instruction count being useful in order to make the machine run faster because there are few instructions fetched, but in modern machines we can get by that by using caches rather than implicitly reducing the number of instructions. Another famous argument was that it's better to match the design of the instruction to high-level languages and let the computer do the work rather than the compiler do the work. Well, it often turned out that trying to do those kind of high-level language instructions was counterproductive because the instruction could rarely be used. The special cases in which that instruction was designed for either never existed or changed as compilers changed and languages changed in particular. The counter-argument for risks is that if you in fact make the instructions simpler, then you can not only reduce the number of cycles per instruction, but reduce the cycle time. So what risks are doing are lowering the cycles per instruction. At the same time, though, they're raising the instruction count. The big breakthrough came in recognizing that using the RISC implementation and the high-performance pipelining that we'll talk about later, you can get a much larger effect by lowering the cycles per instruction by factors of 2 to 5 or greater, and the corresponding increase in instruction count is much less. It's 1.5 or 2, or some number like that, and we'll see some measurements that support that later. So although the people proposing CISC instruction sets had the right idea, the numbers were against them. Notice that RISCs are reduced instruction sets. They're not necessarily simple instruction sets, and we'll talk later about some of the complications in some of the more modern RISC instructions. Well, those are some of the trade-offs you get to make in doing instruction set design. How do you make the decision about what to do? Well, the only way to do it for real, because this is not a theoretical exercise, is to measure real applications. And I'll go over some numbers now that have been collected that measure real applications across a variety of architectures, and we can look at how they play. These particular numbers use TeX, which is a formatting language, mostly character and string manipulation, GCC, which is a compiler, and SPICE, which is a numerical analysis kind of simulation language that does a lot of floating point operations. Doing these real-world instruction studies is sometimes frustrating because the measurements vary greatly, and the conclusions you reach will depend a lot on what mix of applications you choose. But if you choose an appropriately rich set of applications, then you can use conclusions which don't vary very much. One of the questions is, how do you get these numbers? And there are several different ways. One is that you can simply write a software simulator. You just simulate the instruction set architecture, which is useful for the case where it doesn't exist yet. And in the simulation, you count things like number of times memory operands are used and so forth. Another way is to add software to an existing processor. If the processor is microcoded, you can add stuff to the microcode that collects statistics about instruction execution. It may slow down the processor, but you don't care. What you're interested in for these kinds of measurements is not time, but counts, the number of times things happen. Another way to do it is that most instruction architectures these days have an instruction trapping mode that allows you, for debugging purposes mostly, to take a trap or an interrupt in between the execution of every instruction, in which case you can look at the instruction being executed, decode it manually in the software, and figure out what it's doing and add appropriate counters to your statistics database. You can't do any of those, then you can always go in and add hardware instrumentation, wires and probes. In the old days of mainframes, this was a fun thing to do, and there were companies that made their livelihood by building hardware probes that you could attach to various pins in your computer and measure the performance and where the time was going and the execution rate of instructions and so forth. That gets to be much more difficult when the processor is entirely embedded within a single IC, and you can't get access to anything except the pins on the outside. Okay, so a bunch of those measurements were done. You don't have to do them. Let's look, for example, at what addressing modes are most common. This is data from the VAX, which is a good one to use to look at addressing modes because it has every addressing mode known to mankind. So, what in fact does it use? Well, the first thing to notice is that, remember, the top two on our list of addressing modes were not memory accesses, but either register accesses or immediate accesses. Well, lo and behold, the vast majority of addressing modes are either register modes or immediate. Is there a question? You don't have that slide. Yes, you don't have that slide. What you have is a slide which is a composite of two different slides from the book, and you will have this slide in the next handout. What you have is a slide that expands only the memory reference part and shows how they distribute and add up to 100%. What I did for this slide was to combine that with the non-memory reference modes to look at them as a whole. So the non-memory reference addressing modes, in fact, correspond to what? 50 plus 20, maybe 70% of the accesses. So obviously in designing your computer, you want to design encodings and implementations for those modes which are efficient. Of the addressing modes that actually reference memory, the two that are most important are the displacement and the register deferred or register indirect mode. Remember, these are basically both the same thing. The register indirect is the mode where the displacement is 0. So obviously, if you were to choose any single addressing mode for your machine, that's the one that you ought to use. Most of the others are in the noise, and not implementing them unless it's extremely expensive to do in software is probably not a risk. Bad choice of pun. Probably not a poor choice to make. But given a particular application, that might not be true. Notice that for SPICE, which does a lot of array accesses, that in fact the scaled addressing mode, which is used for array accesses of word-like quantities, turns out to be an important one. And in fact, we'll look later at some evaluation of this mode and what it costs in a machine that doesn't have it to implement it in the more primitive addressing modes that the machine does have. Looks like we're about out of time, so I'd better stop there. We'll continue next week. No, we'll continue on Thursday.
What do these do?